So what we are going to do is we're going to use the Z-transform to realize filter banks with critical sampling and perfect reconstruction. So the problem we've seen with ideal filter banks is that brick wall filters, they are not realizable. It would imply an infinite delay. So our approach is to find a suitable mathematical description for realizable perfect reconstruction filter banks. Well, here we'll take a look at the analysis side, so the analysis filter bank, and we can use noble identities to exchange filtering and downsampling of each subband. So for example, if we take just one subband and we have filtering and downsampling, and we can also use noble identities, and we will have downsampling and then filtering. And you can have a look into a detailed class about the noble identities and filters from our advanced digital signal processing, also given by Professor Schuller at the TU UMNAL, and we also have the notebooks and tutorials, and you can take a look about the noble identities. So what we see is that the left hand side with the downsamplers can be seen as a serial to parallel converter into blocks of length capital N. And what we do is that we obtain blocks or vectors of length N for the signal X and the filter H, each containing polyphase components. The Z-transform vector of this polyphase components of input X is given here. So now we are on the Z domain and we have polyphase components of input X. And the Z-transform vector of the polyphase components of the filter is given here. So here, H of K of Z, we're in the Z domain, and we have polyphase components of the filter. And we know that X of N, we have 0 to N equals N minus 1, is given by this formula here, and H N of K is given by this equation here. And we see here we have a C to the power of minus M here, so very important to pay attention. And this shows a representation as vector of polynomials. And observe that a polyphase vector like this can also be written as polynomial vectors. So this is a sum of X of M times capital N, M times capital N plus 1, and so on, until we have N times capital M plus N minus 1. And we see that the vectors in the sum are the blocks of length capital N of our audio signal. The sum takes all blocks of length capital N of our signal and turns them into this polyphase polynomial. So now we are dealing with polyphase and we are dealing in the Z domain. So using this polyphase concept, we will arrange the capital N impulse response vectors Hk of Z of length N into a N times N square matrix. And we use a square matrix because it can be invertible. So we have here our vectors. They represent subbands. So the form of the polyphase matrix for analysis, this is a type 1 polyphase, is given here, and we have a phase and subband indices. And each subband filter, they can be written given by this sum here. This is the phase and this is the subband, and a sum going from N from 0 to N minus 1. So the final equation of the analysis filter bank is Y of Z is equal to X of Z times H of Z. And H of Z is given here. And X of Z is given here. So the output of the analysis filter bank will be X of Z multiplied by H of Z. we see that h of z is the analysis polyphase matrix, that it's a n by n matrix, and x of z is the vector of polynomial that contains the input samples. Mathematically, is a very simple operation for the entire filter bank, including downsampling. So here we have, for example, a block diagram. We have our input, we have our unit delays here, we have downsampling. At this point here, we will have our x of z, then we have our h of z, then we will have our y of z, which is composed by these individual y0 until yn minus 1. So observe that the multiplication with z to the power of minus 1 can be interpreted as the delay of the signal by one sample, and it can be implemented as a delay or a memory element.